Okay, okay.
Okay, so today we're happy to listen to Andreas Rauh, who will be speaking about some comparison of stochastic and interval-based modeling approaches. And I think that most of you already know Andreas, so I don't present him. And thanks, Andreas, we're all ears.
Okay, many thanks, Sylvie, for your introduction. And as Sylvie already mentioned, I will give a comparison in this talk of stochastic and also interval-based modeling approaches, which aim at an online optimization of the fuel efficiency of high-temperature solid oxide fuel cell systems. And in fact, as you can see also on this slide, that's a presentation that I had given at the end of November last year at a conference in Rauh in France. And it's a joint work together with my long-term collaborator, Ekaterina Rauh, who is professor at the University of Applied Sciences in Wismar, Germany. Okay, then let's have a look at the contents of today's presentation. First of all, I would like to give you a brief overview about different possibilities. On the one hand, model-based approaches, and also on the other hand, data-driven approaches that can be used for modeling the electric power characteristic of high-temperature fuel cell systems. Yes, and these different modeling options, they comprise, first of all, equivalent circuit models. They could be static or dynamic neural network models. And the novel approaches in this presentation are especially interval extensions of neural network models, and also stochastic approaches, which are based on a Kalman filter for an online identification of the electric power characteristics, especially the dependencies on the one hand of the gas mass flow that is supplied to the system. In our case, it is pure hydrogen that is used as the fuel gas, and also on the other hand, the dependencies on the electric current. Now, when you want to use these models, for an online optimization of the fuel efficiency, this will lead to the design of some model predictive control strategies. And those model predictive control strategies, they have to take into account, especially of the fact that we do not want to violate the domain of ohmic polarization of the fuel cell, because violating this domain would lead especially to an accelerated aging of the system. And in order to prevent this, we have to identify there's nothing else than the maximum power point of the fuel cell system, which obviously depends on certain influence factors. And these influence factors are the electric current and also the gas mass flow on which they depend. And yes, the two optimization approaches will be discussed in this presentation. One will make use the Kalman filter-based identification, online identification, and the second one will make use of the interval-valued neural network approach, about which I talked at the very first beginning of the slide. Now, let's have a look at some details about the different modeling options that you could take into account in order to perform a description of the electric power characteristic of fuel cells. I think the most well-known and also classic model for representing the electrochemical behavior is to introduce an electric equivalent circuit model. And this equivalent circuit model takes into account various directed current or voltage sources here. Those sources denoted here by UN. And the index N stands here for nothing else than the Nernst voltage in this case, which is in the ideal case, in the open loop case, the source for the open circuit voltage of the fuel cell stack. And in the maximum, you would have, in a series connection of different electric fuel cells, you would have per cell an individual voltage source here, and those voltage sources are then electrically connected in series. Then, as all of you know, the material in the interior of a fuel cell stack has some finite ohmic resistances. And that also means as soon as we're supplying hydrogen to the fuel cell and as soon as the electrochemical reaction starts, an electric current will be produced, and the electric current through the interior of the fuel cell stack will lead to voltage drops over resistances, ohmic resistances, that characterize the material properties in the interior of the stack. Those are those series resistances that you can see here, connected in series with these open circuit voltage sources relying on the Nernst voltage representation. Yes, and additionally, as soon as you have temporal variations of the electric operating point, there will be variations on the one hand of the electric current through the fuel cell stack, and also there's variations with respect to charge carrier transportation. And those transient behaviors could be represented, for example, by these parallel connections of capacitors and also resistors here in this case. Those represent here charge carrier transportation in the interior of the fuel cell stack itself. Yes, and what you can already see is those parameters are quite many, and identifying those parameters, this is possible, obviously. For example, we have presented a few years ago, around 3 years ago, at a conference in Międzyzdroje in Poland, a work in which we designed optimal excitation strategies for identifying the parameters of this equivalent circuit representation. But the thing that makes it very difficult to apply the system model for the control, especially for preventing the violation of constraints on the ohmic polarization, is that all of these parameters that you can see here in the interior, they depend on effects like the temperature, they depend also on the gas partial pressures, and therefore also indirectly on the gas mass flows that is supplying to the system. And this huge amount of parameters on the one hand, and also the possibility to represent very fast variations of the operating points due to this RC subcircuits that you can see here in the interior. These are by far too complicated to realize useful approaches here for the online optimization of the electric operating point. For that reason, one could investigate different, also data-driven models. Okay, one option would be to take into account a static relation between input variables and the electric power here on the right-hand side as the system output. And what you can see directly in this static feed-forward neural network representation is that I introduced something, not a classical output element, but a direct multiplication of the modeled stack voltage UK. The index K here stands for the time instant in an equidistant temporal discretization of the system model. And this voltage is then multiplied here with a measurable electric current in order to represent mathematically the respective electric power. Now, what are the dominant influence factors that are taken into account in the input layer of this neural network? These are selected temperatures, especially temperatures at the gas inlet and gas outlet manifold. That's obviously also the electric current here. These are the gas mass flows at the cathode, which is typically preheated air. Since we're talking about preheated air, obviously also its temperature. And the same also at the anode side. At the anode side, we're supplying an inert gas, nitrogen, and the fuel gas, here hydrogen. And both of them are mixed a priori because before they enter the fuel cell stack. That means they have a common temperature, theta Ag. Okay, and then what you could do is you could represent the corresponding input-output behavior in a quasi-static manner by designing a feed-forward neural network, for example, with sigmoid activation functions like they're visualized here on the slide. And the number of those neurons in the hidden layer could be optimized by techniques that employ a singular value decomposition, which is also mentioned in one of the publications that I have listed here in the very last slide of today's talk. Now, the drawback of this system model is it is twofold. On the one hand, it's not easy to take into account the influence of uncertainty in the input variables and to predict the corresponding uncertainty on the system outputs. That's one thing. The second thing, due to the static input-output behavior, it's very hard to forecast here is behavior that shows some delay phenomena. And typically, delay phenomena occur, if I'm just going back one slide, delay phenomena occur due to the fact that we have a transportation of charge carriers in the interior of the fuel cell stack. Therefore, it makes sense to introduce some kind of memory phenomena. And how you could do this is by introducing nonlinear autoregressive neural network models. And those nonlinear autoregressive neural network models, they distinguish between parts of the input, these inputs that you had already seen on the previous slide, here denoted in the upper gray box. These are the gas inlet mass flows, the temperatures of the gas inlets, and also is the temperature of the inlet manifold and outlet gas manifold of the fuel cell stack. And on the other hand, you could introduce, in this case, it's a more general representation for a multi-input, multi-output system model. You could also take into account a history over a certain window of previous output variables. And in our case, this would be a history over multiple times instance for which we have already collected in previous time steps the information about the voltage in the interior or at the boundary of the fuel cell stack. Yes, and there are two possible options. On the left-hand side, you can see a fully nonlinear representation where you have sigmoid activation functions here for both the measurable system outputs and also for the simulated voltages that are being fed back. And on the right-hand side, a simplified version where we have linear dependencies on the voltages that enter, is here the dynamic representation of, is the variation of the electric voltage and therefore also the electric power of the fuel cell stack. Now in identification, using just point valued data, point valued measurements for the electric voltage at the stack outlet, and also taking into account point valued measurements here for the system inputs. This allows you to parameterize both of these system models. And with our experimental validation by using measured data from a test rig that was available at my former place of work at the University of Rostock, those measurements have shown that the more accurate representation is the one on the left-hand side, where we have the fully nonlinear dependencies also with respect to the electric voltages. And for that reason, we will stick to the left-hand side representation for the remainder of this talk. Now, what we have managed to resolve in comparison with a static neural network representation is we can now represent also delay phenomena. The thing that is still missing here in this representation is how to quantify measures for the reliability of the predicted voltages here, and therefore also of the predicted electric power at the stack outlet. Now, what you could do is you could try to combine this dynamic system representation, this nonlinear autoregressive system representation that you have identified for point value data in such a way that you perform some parallel connection with an error correction network, and this error connection network will be trained by using interval techniques, and this will take into account uncertainty also on measured quantities, and it is also capable on taking into account effects like, for example, imprecisely known system inputs. Now, this slide here lists a few further options, which I do not want to discuss in further detail in the remainder of this talk. One could, for example, combine the static neural network model that you had seen on the previous slides, also with linear transfer function elements in order to represent delay phenomena. And those linear transfer function elements could either be characterized by integer orders, or you could also use, for example, fractional order system representations in order to represent effects that in the frequency domain, for example, do not correspond with integer multiples of phase variations of minus or plus minus 90 degrees over the frequency of one frequency decade. And those are things that one could represent here by using fractional order system representations during the identification stage. And that's, for example, discussed here, such kind of fractional order system representation in the second paper that is mentioned here on this slide, in the paper published in the online journal Clean Technologies. Now, I already mentioned that we want to establish some interval valued error connection networks that we want to combine either with the static or the dynamic neural network representations that have been trained with point valued data, as you have seen on the previous slides. Now, what is my definition here of an interval valued neural network model? An interval valued neural network model will exchange the weights denoted here by W1 and W2, between the input and hidden layer, and also between the hidden and the output layer by corresponding intervals. You could collect them, for example, as a data type in an interval matrix, where each of the matrix entries will be defined by guaranteed lower and upper bounds. And the same also holds here for those bald-faced arrows that denote the bias vectors B1 and B2 in the hidden layer and also in the output layer. They can also be exchanged here by corresponding interval quantities. Now our question will be how to design those parameters, how to identify those parameters, W1, W2, B1, and B2, how to identify these quantities in order to find a system representation where the corresponding simulated system outputs contain all the measured data, the complete measured training data set within the corresponding output interval bounds. Yes, and for that purpose, we're introducing here is first of all the representation here of this point-valued nonlinear autoregressive system model. I think that's a quite nice compact notation here. The vector Q, as we already discussed it, corresponds to the measurable system inputs over a certain window of previous time steps. This window has the length capital M. The same also holds here for this previous data of the corresponding forecasted output voltages of the fuel cell stack, which are included here in the vector W, in the vector Y, again over a window of M time steps. Yes, and the point valued training here is, for example, just being performed by using techniques that are readily available in the neural network toolbox of MATLAB, for example. We're setting up the corresponding nonlinear autoregressive system model. We're minimizing a quadratic cost function here, and this quadratic cost function over the corresponding identification experiment will be minimized by tuning for this dynamic system representation the corresponding weight matrices between inputs and hidden layer, between here the corresponding output variables and the hidden layer, the corresponding dependencies between the hidden and the output layer, and the corresponding bias vectors. Yes, and if the function g here contains the corresponding expressions here that we had denoted previously by the sigmoid activation functions, you can rewrite this expression here in a quite compact form here. Many of the operation here just matrix vector multiplications and the element-wise evaluation of the function g, and element-wise evaluation of a sigmoid activation function, for example, a hyperbolic tangent function. Yes, and the thing that we want to do now is we want to add in an additive manner an interval-valued error correction network to this point-valued NARCS model in order to make sure that all the measured data are then included in the interior of output intervals that you can observe here by the measurements at a real test rate. And as I mentioned previously, let's just go back one slide. The corresponding parameters here of this error correction network are those gain matrices here and the bias vectors, and they are denoted here by the square brackets here. Those are the interval quantities that we want to identify. Now, in the very first step, we're doing this in a very naive manner. Okay, what is the very naive manner that you could do? Okay, just set W1, W2, and also B1 to point-valued quantities. Yes, and then just the corresponding result would be adding a constant error bound B2 to the point-valued NARCS model there. And in this case, you already have achieved to include all the observed measurements in corresponding output interval bounds. Okay, this is a solution of the question I had asked, but obviously it's not a good one. Because what you end up with is those are constant error bounds over the complete operating domain that you had considered, over all possible voltages, over all possible electric currents, over all possible also gas mass flows that you had observed. And that is obviously by far too pessimistic in order to quantify uncertainty. Yes, and for that reason, we initiate the identification algorithm with those constant bounds. Those constant bounds are just, as I mentioned before, these are point-valued quantities here denoted by the subject symbol, plus guaranteed interval bounds. Those interval bounds just take into account the influence here or the uncertainty in the measurements. We are inflating just the output of the NURBS model in order to take into account the corresponding information of the uncertain output measurements. And the further step will now be to use a cost function motivated here also by a least squares optimization procedure in order to reduce the corresponding pessimism. And this is not just as we are doing for the point value training of the classical NURBS model, a deviation between the neural network outputs and the corresponding observed data. But what it will be using then afterwards is also information by this cost function that you can see on the slide number 10 here. It's taken into account information about the width of the corresponding output. Yes, and that's a classical definition of the width of an interval, just the distance between the corresponding supremum and infimum of the corresponding computed interval. Yes, and what we want to do now is we want to reduce the width over all observed data. Since our data has a time dependency, the time index here is directly k, ranging from the very first time step to the end of our identification experiment. And what we want to do now is we want to minimize the sum of all the widths of the corresponding computed interval bounds over the complete identification experiment. Now, what we have to make sure is we have to make sure that the reduction of the width does not lead to the phenomenon that we just get a singleton output. But what we have to make sure at the very end is that obviously the measured data should be in the interior of this computed interval. Therefore, we are introducing here a penalty term that penalizes variables or computed outputs that are outside the computed intervals. That means measurements outside the computed intervals are being penalized here by this additive term. Yes, and the scaling there, if you have a look at the corresponding conference paper, is chosen in such a way at the moment that 0% of outliers are admissible. If you perform this identification, and the identification could be done, for example, by using a particle swarm optimization, you end up with the result here on the left-hand side. We have identified the blue interval bounds here for the electric power of the fuel cell stack, and the corresponding measured data are visualized here in red. Now, what you can see there is, especially for phases in which the electric power is just slowly varying, or maybe even constant, those bounds, if you look here on the right-hand side, for example, they are quite pessimistic. Now, the question for this pessimism is, where does this come from? This comes especially from those operating points where we have very rapid changes of the electric power. Yes, and then in the identification experiment, those rapid changes are really stepwise changes because there was a hard switch of the output resistance of the corresponding fuel cell stack. That means there was a hard change from one electric current value to a totally different one within a few milliseconds. And that's something I would say that can easily be ruled out by means of the operating strategy of the fuel cell system. If we don't change the identification experiment, if we just rely on the same data, we could modify our identification task a little bit. Let's go back one slide. We just have to look at the inside of this penalty term here in the cost function. And this penalty term is just modified in such a way that we are penalizing scenarios in which less than 98% of all the measured data were included in the corresponding predicted outputs. Okay, and that means we're allowing for 2% outliers here. And this 2% admissible outliers just lead to the phenomenon that there's some measured data here, some measured data in the points of rapidly changing electric powers, which are not included in the forecasted blue output intervals. But the rest of the complete identification experiment leads to simulated interval outputs of this neural network extension by means of intervals in which all the measured data, the red data again, are fully included. Now, this was the data-driven modeling approach using an interval extension of neural networks, which is one of the data-driven options that you could take into account to identify the electric power characteristics. Now, the second option that you could take into account is you could try to identify also this input-output behavior with the inputs, the electric current here, summarized in this bald-face vector I, the gas mass flow of hydrogen here in this bald-face vector M. You could use this information also to train or to identify the electric power characteristics by means of a Kalman filter. Okay, how does this corresponding system model then look like? The output equation would be something at the point of time k. We want to represent the electric power of the fuel cell stack in terms of a polynomial representation of the electric current and also the gas mass flow. And for that reason, we have introduced here some vectors here, those bald-face vectors which contain monomials in the electric current and also in the gas mass flow. Those could be interpreted as some kind of time-varying output matrix of our system model. And the corresponding weighting factors are included in this vector x. And this vector x is the one that has to be identified, estimated in real time by means of a Kalman filter. Yes, and as all of you know, a Kalman filter will assume in this case that we're estimating a normally distributed probability density function for this vector x. That means the corresponding mean is more or less the best guess here of the corresponding weighting factors, and the corresponding covariance matrix will give us information about the reliability of the corresponding estimate or the representation here of the electric power. Yes, the system model, there is, because we're just relying here on a data-driven approach, is something like an uncertain integrated disturbance model, which assumes that the vector x at the following time step is more or less the same as the vector x at the previous time step, plus some reasonably chosen zero mean additive normally distributed disturbance. And one of the big advantages is, as soon as you have implemented this Kalman filter, is when those coefficients, and this is naturally the case due to the fast sampling frequency in comparison with the actual variation of the operating points, we have slowly varying parameters x that we're estimating with the Kalman filter. For that reason, it's quite easy to implement the Kalman filter in a robustly converging manner. But you could also use this Kalman filter in such a way that you identify information about whether or not you're in the domain of ohmic polarization of the fuel cell or not. Now, let's assume, for example, that we have a second-order polynomial here in the electric current and also in the gas mass flow. That means the result of this identification of the electric power characteristic would be something like a parabola, which is open to the bottom. And the domain of ohmic polarization would be this domain in which we have a gradient of this electric power characteristic with respect to the electric current that is strictly positive. Yes, and since we have already estimated the corresponding mean value of the probability density function that represents the vector x, it's very easy to express this constraint here is in terms of an online identification of the domain where we have ohmic polarization. And that means admissible operating points for our fuel cell system are those operating points in which this partial derivative, estimated by means of the Kalman filter, is strictly positive. Yes, and the covariance information, as I already have briefly mentioned on the previous slide, gives us information about the reliability of the estimates. That means it's an indicator of the identification quality. Yes, and after this introduction into the theory, let's have a look at real-life measurements. As I already mentioned, those were gathered at a test rig that was also funded by the German Research Foundation. And firstly, I would like to start with the results of a Kalman filter identification without the optimization of the fuel efficiency. That means without using a model predictive control strategy in order to enhance the fuel efficiency. And what you can see there on the left-hand side is in the orange color, the measured electric power. That's exactly the same as measured data that you had seen one slide or two slides before for the training of the neural network. And the corresponding 3 sigma confidence bounds determined by means of the Kalman filter. If I'm zooming in there a little bit, you can see this. Those are the lower bounds here in red, the upper bounds here in blue. Those are those confidence bounds, 3 times the standard deviation, that you could forecast by means of the covariance matrix estimated from the Kalman filter. And now let's pick out 2 possible operating points, those yellow bullets. In the first case here, this point at around 25,000 seconds, that's the left one here, around 3/4 of an hour here after the beginning of the identification experiment. You see that this parabola that I mentioned before here is opening to the downward side here. That's a locally quadratic approximation of the electric power characteristic estimated by means of the Kalman filter. The actual operating point that we observed is this yellow bullet. And you see that we are in the domain. Let's go back one slide. We're in the domain where we have the positive partial derivative here. That means that's an operating point here in which we're still in the ohmic polarization. Increasing the electric current would mean we're surpassing here the point, the maximum power point, and we would also violate here the domain of ohmic polarization. We would end up with an operating condition that is not admissible because of accelerated wear of the fuel cell stack. Now the same statement holds for all of those other points here in the white operating domains. In the gray operating domains, for example, here at the point here, 41,000 seconds, we're at an operating point where we have surpassed here the maximum power point, and our Kalman filter here allows us to identify the inadmissible and undesired operating conditions. Those can be easily detected here. Okay, this was, by purpose introduced here in the identification experiment such that we can check the corresponding robustness here of our estimator. Now, what is the idea to optimize the fuel efficiency in real time? First of all, we do not only want to operate our fuel cell system at a constant electric operating point. Let's assume, for example, that we want to use the fuel cell for a cogeneration purpose of heat and electricity in some island area, for example, where we do not have connections to the electric power grid. What you would have there for the fuel cell is typically a battery buffer, but the battery buffer should be as small as possible. And this directly leads to the goal also to operate the solid oxide fuel cell, which is not fast from its corresponding dynamic behavior, but we want to operate the corresponding solid oxide fuel cell in a dynamic operating condition. And this solid oxide fuel cell stack should track some desired electric power profile here denoted by this index with the Roman font here D. That's the desired electric power profile. Okay, one purpose then will be the actual electric power should be identical in the optimal case to the desired one. Deviations here are characterized here by means of this quadratic penalty term. And our next goal will be to introduce here also a quadratic entry in the cost function, which takes into account information about the consumption of the fuel, in our case, the hydrogen consumption. Those first 2 terms here, I think they are also the very well-known ingredients of a quadratic cost function, which you would use, for example, also in the case of a linear quadratic regulator design. The third term here is a little bit more tricky. This logarithmic term that I've introduced there is inspired by, for example, Beria-Lyapunov function techniques, which allow you to prevent with certainty that the actual electric current surpasses here during the optimization some maximum value. Yes, and where does this maximum value come from? This maximum possible stack current? Yes, it's this current that can be computed by means of Faraday's law, in which the complete amount of supplied hydrogen is fully converted to electricity. And beyond this current value, there doesn't exist any operating point. That means the online model predictive control must take into account with certainty that we have some kind of repelling potential that pulls us into the interior of the admissible operating domain. And this is being made sure here with this infinitely large term here at the barrier, in the case that we are reaching here an electric current that becomes equal to this maximum value. This is an infinitely large barrier, and this will pull us back into the admissible operating domain. Okay, obviously, you could also reformulate this expression here as the corresponding minimum required gas mass flow that is required if you're specifying some electric current as the corresponding system input. Now, what we have in this scenario is we have a system model with two inputs and one scalar output. Those two inputs here are the electric current here on the right-hand side. We can specify this current. And we have also the gas mass flow as the second input into our fuel cell system. The output is the actual electric power. Okay, and now what we could do is we could use, for example, some gradient-based update of the vector-valued control strategy. As I just mentioned, the control input vector consists of current and gas mass flow. And what you could do now is you can use gradient-based techniques inspired, for example, by Newton method, you apply them online. And all of those techniques make use of an estimation of the gradient vector, the gradient of the cost function with respect to the electric current and also the gas mass flow. If you have a point-valued system model, for example, resulting from a Kalman filter, what you would have then at the end is those are point-valued estimates here for the corresponding partial derivatives. The values here, this P electric in the evaluation at the point of time K is being replaced here by the measured quantities. We have the desired power and the measured quantities here, the estimated quantities of the Kalman filter, they are being used to, let's go back 2 slides here, to this expression here. They're being used to represent information about the corresponding gradients of the electric power with respect to variations of the electric current and also the gas mass flow. Yes, and as typically in some kind of model predictive control procedure, you have to specify the prediction time horizon over which you're evaluating this expression. And yes, that's at the end quite simple to implement, and we can adapt the corresponding system inputs here. And one trick that you could do, for example, for also smoothing the corresponding variations of the system inputs would be to implement a slow PI controller, that makes sure at the very end that we have stationary accuracy of the desired and the corresponding actual electric power. Now, let's have a look at the interval-valued neural network model that we had. What is the fundamental change? The fundamental change would be that the forecast over some window into the future, and this window into the future is denoted here by NC time steps, is the corresponding forecast of the electric power would be interval quantities. Those interval quantities, as we have discussed before, depend on the system inputs, on the gas mass flow, and also on the electric currents. That means the forecasted cost function here over the time window into the future will become an interval quantity. Okay, and without a detailed derivation of the corresponding expression that you can see on this slide, there are 2 things that we have to do. The first thing that we have to do is we have to compute bounds on the partial derivatives of this cost function with respect to the system inputs, the gas mass flow and the electric current. That means this will be some kind of interval valued gradient vector that we end up with. Okay, we computed it here just for ease of simplicity here in terms of increments of the variations of the system inputs, but you could also use absolute values here. But using the increments allows us, yes, to directly take into account also a penalty term that is smoothing the system input. That means that we're just preventing here rapid changes of the corresponding system inputs, which may minimize the cost function, but which are undesired from a practical perspective, just by rapid opening and closing, for example, the gas valve. And we have now the corresponding interval extension of the gradient vector. And as motivated, for example, by a Newton method or also by the gradient descent method, we could use this gradient information to minimize the corresponding interval valued cost function here in a set valued context in such a way that we're computing the corresponding system inputs. And yes, the evaluation of the partial derivatives is here done in this case by using algorithmic differentiation. And yes, since we only need the first order partial derivatives here, it was very easy to implement this, for example, using the IntLab toolbox directly in MATLAB. Yeah, and in the reference that I had quoted in the conference paper, you will see why we had used here the supremum here. The supremum here of the corresponding interval quantity here is the one that leads to the most robust control update in this case. Yeah, and the plus symbol here is just the pseudo inverse here, or you could say a minimum norm solution here of the corresponding minimization of the corresponding cost function within one update step. And this also leads me to the final results of the optimization. And before we're having a look at a comparison between the Kalman filter-based solution and also the neural network solution, let's have a look at some operating phase in which we're operating the fuel cell stack just in an open loop manner. And what I just did is I just used the first 1000 seconds of this experiment. This is up to the vertical dashed line. I checked the corresponding measurements for the electric voltage, the electric current, computed the corresponding electric power. And using the interval extension of the neural network, we can directly quantify here for this corresponding measurements an interval of the fuel efficiency. Yes, and in average over this window of the first 1000 seconds, we had effectively converted around 15 to 16% of the supplied chemical energy included in the hydrogen into electricity. That means that's not a very good efficiency factor. But this is a typical result that comes out if you just perform naive operation of the fuel cell stack. Now, what we could do is we are activating the control at the vertical dashed line or the vertical dashed time position here. And if we're just using current state information estimated by means of the Kalman filter, you see you will end up with tracking some desired power profile. Yes, this is here, is hidden below the colored lines here. And what you can see is we have in the mean, if you look at the power tracking error, except for some phases in between where we have, due to variations, for example, of the measured temperatures of the fuel cell stack, some oscillations, we have a quite nice tracking of the desired electric power profile. The variations here of the gas mass flow and of the electric current here are depicted on the right-hand side. And this already leads to an enhancement of the fuel efficiency. What we compared here, also on the left-hand side, we have to zoom in again. We see the forecast of the accuracy of the corresponding electric power model on the one hand in green, and the light blue curve as the 3 sigma bounds computed by the Kalman filter. Yes, and they're a little bit tighter than the corresponding bounds that you would obtain here by the interval valued neural network model. The interval neural network model is obviously something that is more robust, but they are good in good coincidence, those models to each other. Now, the question is, why hasn't the enhancement of this fuel efficiency been so large than we may have hoped for. The reason for this is very simple. It's just a one-time step ahead optimization that we used. With help of the neural network model, we can look a few seconds or also a few minutes into the future. This allows directly for smoothing the control action on the one hand. This helps for smoothing also the corresponding tracking errors. On the one hand, also to reduce the tracking errors. And on the other hand here, as you can see with this 68% at minimum, a significant enhancement of the use of the electric energy or of the chemical energy to convert it into electric energy. That's the correct way, I should say it. And it's very easy, for example, to use also is the information from this Kalman filter-based solution now in order to rule out violations of the domain of ohmic polarization, because we can use this estimate as some kind of artificial barrier that we're introducing here in order to make sure that our electric current will be limited to the above by means of the corresponding boundary that results from this gradient expression here, where let's go back to slides here, where we had the positive gradient here of the electric power characteristic with respect to the actually chosen electric current as the system input. Yes, and this already leads me to the conclusions of this presentation. What you have seen is, yes, various different options how to model the electric power characteristic of fuel cells, especially two data-driven options. One data-driven option using the Kalman filter, the other one using a neural network. And both of them have different robustness properties, and especially the robustness properties and also the predictive capabilities of the nonlinear autoregressive system model in combination with the interval-based quantification of uncertainty, yes, leads to a robust possibility for an online optimization of the fuel efficiency. Yes, and from that point of view, I think that's just a brief look at the outlook. Obviously, it makes sense also is to enhance a little bit the training of the neural network models. One thing is to take especially into account the derivative information that we had already seen in the Kalman filter also for training the neural network. And the second thing is obviously to perform further real-time and also real-life validation experiments for various types of fuel cell systems. What I presented here is the control of a high temperature solid oxide fuel cell. But what one could do, for example, is in the context of high temperature solid oxide fuel cells, one could even aim at optimizing the overall power output by optimizing the production of heat and electricity in this cogeneration framework at the very end. So that's all from my side. You can already find the corresponding slides on the webpage of our seminar. If you're interested in those related publications that I previously mentioned, just have a look at the very last slide. And yes, you can download the corresponding PDF files from ResearchGate, from the publisher web pages, or from the personal web page. Many thanks for your attention.
Thank you, Andreas. Thank you very much for this very nice presentation. I'm sorry I was late because of my connection to Zoom. So we have time for
no problem at all. Sylvie took over the duty to chair the session at the very beginning.
Okay, so thank you. So we have time for questions. I want to start. Who has some questions, please? Maybe I can start. Could you please put slide 10, please?
Slide 10?
Yes. So what do you mean by a maximum percentage of outliers can be tolerated by a suitable choice of the matrix P? Okay, how to do?
Yep, that's the thing. I think it's even better to explain on the next slide here.
Yes.
The initial optimization procedure was implemented in such a way that all the measurements, that means all of those red points that you can see on the left-hand side, that they are fully included in the output intervals determined by the neural network model. Now, what you could do is you could start to reduce the corresponding width of the intervals in an intelligent manner that you allow some of those measurements to be outside. And the values that are allowed to be outside are those, yes, with the largest deviation from the corresponding interval midpoints. And in order to achieve this, we're just lowering this penalty term here, this additive term here in the right-hand side on the slide number 10, in such a way that we allow for a few percent of outliers, for example, 2% of outliers. That was shown on the right-hand side of the previous slide.
Okay, so as an alternative, is it possible to detect and to discard outliers?
That's very hard to say, because the thing is, the question is it a real outlier, or is it maybe something, if you look at this slide again, that results from a rapid variation of the operating conditions? For example, if you have a step-like change of the electric current just by switching the ohmic resistance at the outlet of the fuel cell stack. And those points typically, yes, activate some transient operating phases that are not being accurately captured is by this feedback of previous output estimates. And there, I think it's really a domain where outliers cannot be distinguished from rapid changes of the operating conditions. What one could do is, you could do some kind of, let's say, pre-filtering that you identify those rapid changes, that you exclude them from the identification experiment. And then I think you can, at least with some degree of confidence, some level of confidence, you could distinguish between outliers and let's say actual variation of the operating conditions. But it's really more or less when we're going back here to the system model, where we have this window of previous measurements that you're taking into account. The sampling frequency is not high enough to capture really this rapid variations here, which are outside the scope of this model. And those have to be excluded first, and afterwards, I think you can identify outliers.
Okay.
But I didn't try out so far. That's one of the points, for the future. Maybe also for the plans of our joint collaboration, for example, with respect to identifying also battery systems. I think there it will really make sense to investigate such strategies, how to reliably distinguish between something that is not modeled and something that is a real outlier.
Yes, I completely agree with you. Thank you, Andreas. So are there some other questions, please?
Yeah, I see Xu has raised her hand.
Yeah, sure.
Yeah, hello, I have a question in the slides for, I think it's 19, the slide 19 that we showed. This one, yeah. So first of all, we can see that at the time of 0.5 or 0.7, there's some oscillation in the in the first and in the second power tracking error, and also the optimized fuel cell power. So why they have these oscillations at this time?
That's a little bit a tricky question there. It is partially related to the thing that Tarek just asked, because there could be an outlier in the measurement.
Yes.
And this outlier could lead, to triggering some oscillation that you could try to prevent by longer prediction windows in the model predictive control. That's one answer. The second answer is, and this is a more, let's say, tricky thing, how I performed this comparison between the Kalman filter and also the neural network model. The input data are measured data. The data are, for example, measurements of the electric, the gas temperatures of the gas mass flows here. They stem from the experiment. But in order to make both approaches comparable, we simulated here the corresponding variations of the gas mass flow and also the variation of the electric current. That means it's a combination between simulation and experiment on this slide. And what we have in this experiment is, for example, also some outliers in the measured, for example, temperatures at the gas inlet manifold. And that's something, yes, that can only be taken into account in a closed loop operation when you have the complete controller. The complete controller, on the one hand, takes into account the electric power control, and on the other hand, also a consistently designed controller for the thermal behavior of the fuel cell. And that's something that is, yes, on purpose not included in this model. It's a perfect question that you asked here. But I think it's impossible to avoid such behavior in this case. If you have partially measured data that you're interfacing here with a simulation where you don't have the feedback from the electrochemical side back to the thermal behavior in this case. And if you would have this, it would be ruled out, certainly, because then you have this interconnected nature of this multi-physics system.
Yeah, okay, got it. So I have a second question in the next slides. So the page 20. No, not 20, I forgot it, but you have the comparison that maybe it's the 18, could I see it? Yes, here, for the first photo, the first figure, the optimized, here, the optimized fuel cell power. Yeah, here we can see that for the range, the green line and the blue line, you use an interval range that you use the 3 delta. And how we can choose this range, and could we change to a smaller value or bigger value? So,
okay, that's chosen systematically by the design of the Kalman filter. We have to go back to this slide here. Because what we have is, this is more or less the output equation that is used in the Kalman filter. So we have 2 types of uncertain quantities. We have, yes, the weight vector x that we want to estimate. This is represented in our case by a normal distribution.
Yes.
And we have measurements of the electric current and also of the gas mass flow in order to set up those vectors of monomials of current and the corresponding gas mass flow. What I did here is, those are measured quantities. We have information from the data sheet here concerning the current sensors and also the mass flow controller.
Yes.
We have corresponding information about standard deviations, for example. And what you could do is you could easily compute the corresponding second moment of the probability density function of the term here in the round brackets. And this is then, it's a little bit concerning the Kalman filter, it's a little bit misuse of the Kalman filter, I have to say. We're using this as a point valued quantity. And the bounds of the uncertainty that we're getting from the second moment that I computed is then being added as some kind of virtual additive output disturbance. And that's just an approximation here in order to stick to the linear estimation scheme, because otherwise you would have some multiplicative couplings between uncertain measurements and the quantities to be estimated. That means directly you would have to use a nonlinear filter if you want to perfectly handle this. But just because we have a very fast sampling here in our system, I didn't detect anything that doesn't look really reasonable in the estimates. It was just replacing the corresponding term here in the round brackets by a point valid quantity, approximating the uncertainty by an additive Gaussian noise. this is how I did this systematically and using the Kalman filter formulas. You get those bounds that you had seen.
Okay, got it. Thank you. That's all my questions. Thank you.
Thank you.
Thanks for your question.
Are there other questions, please, in the audience? So I think no. So thank you, Andreas. Maybe you can stop here for today. Thank you very much for this very nice presentation.
Okay, and thanks also to all the audience for attending today's session. And yes, the last thing I have to say now for today is have a nice Friday evening, Friday afternoon, and have a nice weekend. And we'll see each other again on Friday in 2 weeks after the Easter holidays.